Hello everyone, my name is Herta Montoya. I am a PhD student at Purdue University.
Hello, my name is Yuguang. I'm a postdoc at Purdue University.
We will present the modular coupled virtual testbed developed by the RETH team. Deep space habitation is a grand challenge. Space habitats are complex systems that may exhibit unpredictable interactions and interdependencies due to the demands of extreme environments. The modular coupled virtual testbed, or MCVT, represents a notional real habitat consisting of various systems and human and robot agents. All these subsystems, like structural, power, interior, and exterior environment, to name a few, are closely interconnected, and its modeling concept is approached as a system of systems to study their dynamics and interactions comprehensively. The development of MCVT is not to provide the design of a specific habitat, but to allow the team to carry out a wide array of quantitative research on resilience and autonomous operation of deep space habitats. What is MCVT? MCVT is a real-time, physics-based simulation framework aimed to capture unpredictable interactions in a high degree of technical complexity. In addition, it serves as a control-theoretic approach to resilience, providing the team a testing plan to refine and evaluate our control effectiveness metric. It also enables our team to identify the health management requirements for an autonomous smart habitat, and it provides the platform to develop our cyber-physical testbed and reflective framework for performance management. The real-time simulation environment of MCVT is written in MATLAB and built upon its Simulink platform to model and simulate the integrated habitat as a system of systems. The 6 system blocks on the right-hand side represent the 6 physics-based models of the current MCVT: structural, power, ECLIS, interior environment, health management and agent, and the exterior environment. By generically decomposing each MCVT subsystem, it was possible to identify and categorize the main interface elements and interactions. The MCVT subsystem interactions are the following: cyber and physical interdependencies, all rigorously handled within the coordination block on the left-hand side. Disturbances from the exterior environment, and interventions from the command and control and agent system. We adopted the network representation technique, known as the design structure matrix, to enhance and facilitate the modeling and integration of the MCVT subsystems. The primary purpose of the design structure matrix is to identify data flow, interface conditions, and operational modes. An off-diagonal X mark indicates the presence of an interaction, while an unmarked cell signifies the absence of it. 2 design structure matrices, one crude and one dormant, were developed for MCVT. Both matrices are part of a simple platform with interaction specifications. This platform graphically specifies an interaction and directly links the user to a page that provides interaction specifications, such as the type of interaction, size of the signal, sampling rate, signal units, and any helpful additional notes. The design structure matrix was a critical tool to identify operational dependencies and facilitate integration among subsystem models.
Built upon the design structure matrix, we also established an implementation table to clarify model requirements, track development progress, and facilitate integration by isolating potential errors. A total number of 8 critical items are listed to check, were organized in 4 phases, such as standard formats, sample time consistency, plan execution, and code compilation. Each subsystem has different dynamic behavior and different computation costs. Therefore, they have different optimal simulation rates. We have developed multi-rate simulation to meet their requirements and minimize computation time. It is realized by carefully handling rate transition between base rates and specific subsystem rates. In the end, it can save up to 90% of computation time without compromising high-fidelity simulation. Furthermore, to manage the new change from developers and fix bugs found by users, we have rigorous version control using GitHub, coordinating the developments among more than 5 task groups. So far, we have built 3 versions for end users, and each one is made by going through a systematic flowchart involving the interactions with model developers, model integrators, and subsystem leaders. Finally, to host and simulate the MCVT in real time, we also build digital infrastructure, which consists of several real-time systems and high-throughput communication network. Extensive testing has been carried out to evaluate their both sequential and parallel execution. The performance profile for different communication options are also made, including delay and bandwidth. To demonstrate the overall functionality of MCVT and digital infrastructure, an example scenario is executed in one host PC and 2 real-time systems, which are interacted through UDP communication. It is accelerated to include many interesting cascading events within 1-minute simulation. Particularly, after meteorite impacts, the structure is damaged, and internal temperature and pressure drop accordingly. Then the Eclipse is then working hard to maintain the interior environment. Upon receiving the damage detection signals, the agent moves to and repairs the structure. Eventually, the habitat system recovers back to the normal conditions. Thank you.